Welcome to the session on numerical differentiation. When the function y equal to f of x is exactly defined, such as y equal to x raised to n, y equal to e raised to x, y equal to cos x sin x, etc., we can find dy by dx by the calculus method. But sometimes the function y equal to f of x is defined in the tabular form. That is, the function is given by the values y0, y1, y2, etc., yn corresponding to the values x0, x1, etc., xn of x. In such situations, the actual value of f of x cannot be found out, but f of x is approximated by any convenient interpolating polynomial p of x. Then dy by dx is found out as p dash of x. The process of computing dy by dx at x equal to some xk by this method is called numerical differentiation, where x0 lying between xk lying between x0 and xn, or xk is very close to xn or very close to x0 if it is outside the range x0 xn. If the values of x are equally spaced, we can use the forward interpolation formula or Newton's backward interpolation formula to find the corresponding interpolating polynomial. If the values of x are not equally spaced, we can use the divided difference formula or Lagrange's interpolation formula. Even though f of xk is approximated by p of xk, the derivative f dash of xk need not be equal with p dash of xk. P dash of xk can be assumed to be a good approximation of f dash of xk only if the differences of f of x of some order are equal. Here we shall discuss the values of derivatives of y based on Newton's forward interpolation formula. When n plus 1 pairs of values x0, y0, x1, y1, etc., xn, yn are given, Newton's forward interpolation formula takes the form y is equal to y0 plus u by 1 factorial into delta y0 plus u into u minus 1 by 2 factorial into delta square y0 plus u into u minus 1 into u minus 2 divided by 3 factorial into delta cube y0 plus u minus 1 u minus 2 into u minus 3 divided by 4 factorial into delta raised to 4 y0 plus etc., where u equal to x minus x0 divided by h. H is the interval of differencing, which is a constant. Now, we differentiate this formula on both sides. We get here y is a function of u, where u is a function of x. Therefore, we can use the function of function rule for differentiation. Here du by dx equal to, here u equal to x minus x0 divided by h. Therefore, du by dx, derivative of u with respect to x, is x0 is a constant, h is a constant. Therefore, 1 by h into derivative of x minus x0 is 1. that is du by dx equal to 1. Therefore, dy by dx can be written as dy by du into du by dx. That is equal to du by dx is 1 by h into dy by du, which is equal to 1 by h into y naught is a constant, therefore derivative is 0. Here derivative of u is 1, 1 by 1 factorial is 1 itself, delta y naught is a constant, plus here u square minus u, derivative of u square is 2u minus derivative of u is 1, that is 2u minus 1 divided by 2 factorial into delta square y naught plus 1 by 3 factorial into, here the derivative we use the product rule, obtain 3u square minus 6u plus 2. We differentiate this term u into u minus 1 into u minus 2 by the product rule of differentiation. We get 3u square minus 6u plus 2 divided by 3 factorial into delta cube y naught plus 1 by 4 factorial into derivative of this product is 4u cube minus 18u square plus 22u minus 6 delta raised to 4 y naught plus etc. 1 by h is common, therefore we use the bracket. Now, we differentiate this once again, we get d square y by dx square, the second derivative of y with respect to x, which is equal to d by dx of dy by du into du by dx. Which is equal to 1 by h square, du by dx is 1 by h, therefore 1 by h into 1 by h is 1 by h square into delta y naught is a constant, therefore derivative is 0, 2u minus 1, derivative of 2u minus 1 is 2, 2 by 2 factorial is 1, that is delta square y naught plus here derivative is 6u minus 6, 3 factorial is 6, therefore 6 and 6 cancelled, the remaining term is u minus 1, u minus 1 into delta q y naught, 1 by 3 factorial into u minus 1 delta cube y naught, sorry 1 by 3 factorial is cancelled, u minus 1 into delta cube y naught plus the next term is 1 by 12 into, here derivative is 3 into 4 u square, 12 u square minus 36 u minus 22, 4 factorial means 1 into 2 into 3 into 4, that is 24. Therefore, we get 1 by 12 into 6 u square minus 18 u plus 11 delta raised to 4 y naught plus etc. This is the second derivative of y Now, we differentiate once again with respect to x, we will get the third derivative as d cube y by dx cube is equal to 1 by h cube into delta cube y naught plus 1 by 2 into 2u minus 3. Delta raised to 4 into delta raised to 4 y naught plus etc. This is the first derivative, this is second derivative, and this is the third derivative. We can find the higher order derivatives also. These expressions for derivatives may be used to find the first three derivatives of y at any point x equal to x k, where x k is lying between x naught and x n, or x k is very close to x naught or x n if it lies outside the range x naught comma x n. When x equal to x naught, these three formulae will become dy by dx at x equal to x naught. If x equal to x naught means u will become 0, because u is x minus x naught divided by h. If x equal to x naught, u will become 0. Therefore, the first derivative will become 1 by h into delta y naught minus 1 by 2 factorial into delta square y naught plus 2 by 3 factorial is 1 by 2, sorry 1 by 3 into delta cube y naught plus etc. That is dy by dx is equal to dy by dx at x equal to x naught is equal to, we can use the differential operator. The symbol of differential operator is capital D. dy naught is equal to 1 by h into delta y naught minus 1 by 2 delta square y naught plus 1 by 3 delta cube y naught. Next is minus 1 by 4 delta raised to 4 y naught plus etc. When x equal to x naught, the second derivative d square y by dx square will become capital D square y naught. We have to use this symbol, which is equal to 1 by h square into delta square y naught minus delta cube y naught plus 11 by 12 delta raised to 4 y naught minus etc. And the third derivative will become d cube y by dx cube at x equal to x naught is capital D cube y naught, which is equal to 1 by h cube into delta cube y naught minus 3 by 2 delta raised to 4 y naught plus 7 by 4 delta raised to 5 y naught minus etc. From this we can write the derivatives as capital D equal to like this. Capital D is identically equal to 1 by h into delta minus delta square by 2, that is 1 by 2 into delta square plus 1 by 3 into delta cube minus 1 by 4 into delta raised to 4 plus etc. This can be written as from this we can write capital D square is equal to 1 by h square into delta square minus delta cube plus 11 by 12 delta raised to 4 minus etc. And from this third derivative we can write d cube equal to 1 by h cube into delta cube minus 3 by 2 into delta raised to 4 plus 7 by 4 delta raised to 5 minus etc. Capital D means the differential operator, delta is the forward difference operator. We just proved in the beginning of the finite differences this result we just proved. Now, we have an example. We are given a data and using this data we have to find some derivatives. The data is x values are 1.5, 2, 2.5, 3, 3.5 and 4. The corresponding y values are 3.375, 7, 13.625, 24, 38.875 and 59. Here the arguments are equally spaced. Therefore, we can use the forward interpolation formula. We have to evaluate f dash of x and f double dash of x at x equal to 1.5. F dash 1.5 and f double dash 1.5. We have to evaluate the values of derivatives at 1.5 and first derivative and second derivative at 1.5. Note that here the x naught is 1.5, this is x naught, x1, x2, x3, x4 and x5. The corresponding y values are y naught, y1, this is y2, y3, y4 and y5. Here we have to evaluate f dash. First we evaluate f dash at 1.5. Here 1.5 is our x naught. Therefore, we can use the formula d equal to 1 by h into delta minus delta 1 by 2 delta square plus 1 by 3 delta cube minus 1 by 4 delta raised to 4 plus etc. First of all, we have to construct the forward difference table. The first order differences are 7 minus 3.375 which is equal to 3.625. Next difference is y2 minus y1, that is 13.625 minus 7 which is 6.625. Next is 24 minus 13.625 which is 10.375. Next is 38.875 minus 24 which is 14.875. The last first order difference is 59 minus 38.875 which is 20.125. These are the first differences. The second order differences are 6.625 minus 3.625, which is 3. 10.375 minus 6.625 is 3.75. Next second order difference is 14.875 minus 10.375, which is 4.5, and 20.125 minus 14.875 is 5.25. These are the second order differences. The third order differences are 3.75 minus 3, which is 0.775. 4.5 minus 3.75 is 0.75, and 5.25 minus 4.5 is again 0.75. The fourth order differences are delta raised to 4y, both are 0, and the fifth order also is 0. Here 5 values are given, therefore, there are 5 differences. Here 6 values are given, therefore, there are 5 differences. Therefore, this is y naught, this is delta y naught, this is delta square y naught, this is delta cube y naught, this is delta raised to 4 y naught, and this is delta raised to 5 y naught. Substituting these values in this expression, we get here h is equal to 2 minus 1.5, that is 0.5, h equal to 0.5, and therefore, the first derivative capital D is equal to that means the first derivative at x naught dy by dx at x naught means 1.5, x naught x equal to x naught means x equal to 1.5, that is equal to 1 by h into, that is 1 by 0.5 into delta means delta y naught, that is 3.625 minus 1 by 2 into delta square y naught is 3 plus 1 by 3 into delta cube y naught is 0.75 plus all the the next two differences are 0, therefore, the corresponding terms are 0. On simplification, we will get this as 4.75. This is the first derivative, that is dy by dx at x equal to x naught is at x 1.5. Now, the second derivative at x equal to x naught is we use the expression d square is equal to 1 by h square into delta square minus delta cube plus 11 by 12 delta raised to 4 minus etc. Therefore, the second derivative d square y by dx square at x equal to x naught is 1.5 is equal to 1 by h square, that is 1 by 0.5 square into, here delta square means delta square y naught, that is 3 minus delta cube y naught is 0.75 plus 11 by 12 delta raised to 4 y naught is 0. The next term also equal to 0, because the fifth difference is 0. On simplification, we will get this as this is equal to 9, that is the first derivative at x equal to 1.5 is 4.75 and the second derivative is 9. We use these expressions because we want to calculate the derivatives at x naught. Therefore, we used these two expressions. Now, let me conclude this session. In this session, we discussed the derivatives using Newton's forward interpolation formula. Thank you for listening this session and have a nice day.